Hi everyone, this is Dayuan. I hope you guys are doing well, and today I will do a quick midterm review. I hope it helps. Actually, the first lecture for this class is digital logic review, but we think it will not be a part of this midterm because Professor Ivan he mentioned that the first lecture it helps for everyone to review what has been covered in CMSC411, so it will not be a part of the midterm. We can just skip it. And then we'll begin with the second lecture, which is arithmetic. So for arithmetic circuits, it tells us something about the hardware for those circuits, for either multiplier, division, floating point arithmetic, and ALU. Firstly, we begin with adder. We need to know the full adder design. That means we need to know the truth value table. We need to know what's the difference between RCA and CLA. And then for multiplier, we need to know the basic idea. For the algorithm, it has the hardware figure, which is in Professor's slides. So I hope you can look at quickly and get familiar with the basic idea. And also the hardware version 2 and hardware version 3 and how they improve it. And that is the multiply standard numbers and also Booth algorithm. For the multiply standard numbers, actually what we did is just to do it as what we do for unsigned members, and after that we apply sign on it. And the Booth algorithm is also used for multiply standard numbers, but it makes it easier to deal with this problem. Next is the division. Of course, we also need to know the basic idea and how to combine the multiply and divide together. Next part is floating point arithmetic. For this part, in Professor's slides, it provides us a floating adding hardware example. We can go through it quickly to get the basic idea. The next part is ALU. In Professor's slides, it also gives us the hardware structure of ALU. What we need to do is just to know it, and for this lecture, I think maybe it will have some multiple choice questions to make sure you understand the concept of them. Then next is the lecture about performance. I think this lecture will be more important for previous lecture. Firstly, the important point is about Moore's law. Make sure you understand what will double. It's not the performance will double. It's not power will double. It's not the price will double. It's the number of transistors that could fit on a chip would double every year or every 2 years. Here in this class will take the 2 years. So Moore's law is the number of transistors that would fit on a chip would double every 2 years. And then is the energy. It has a formula for it. And then is the power. Power is the energy time with frequency switched. Next part is the performance. The performance is the 1 over SQ time. This formula is a very important formula. It's very basic for further other formulas. So make sure you can memorize this one. When we talk about execution time, usually we don't say the execution time of a computer because the I/O system, the disk, or they vary from computers to computers. So usually we say the execute time of one chip. In this case, the execute time will be CPU time. And then is the CPU time. Here are some formulas related to CPU time. The CPU time is cycles time clock cycle time. Usually the clock cycle time is clock rate, so CPU time is cycles time clock rate. And it also is CPI, cycles per instruction, time IC, instruction count, time clock rate. But CPI times IC, cycles per instruction, time instruction counts. That's cycles. That is, you say that is cycles. So, and the second part, clock rate doesn't change, so it's still cycle time clock rate. And also about the CPI is cycles per instruction, so we use cycles over instruction count. And then is another formula is CPU time is instruction over program, time clock cycles over instructions. This part is actually CPI is cycles per instruction, right? This part is actually CPI. As this part is actually what we say I say here. And the third part is seconds over clock cycle is actually what we say clock rate here. So those formulas, they are actually same. So we not only need to know those, we also need to know the different transform of those formulas. And make sure you are familiar with all those transforms. Sometimes we need to use the first one, sometimes we need to use the third one. So we need to get familiar with all transforms of those formulas. And then is how to improve performance, how to calculate it. In professor slides and also in class activities and homeworks, there are some examples. Make sure you go through them one by one and make sure you know how to calculate the performance improvement. For example, if I have two chips or two design versions, which one is faster, which one has better performance, we need to calculate the CPI or execution time. And then is Amdahl's law. Amdahl's law is more about speed up. When you make some question about speed up, you can use this formula. The speed up is old execution time over new execution time. This is a very basic formula, and you can always use this one when you meet the speed up questions. It also has some transforms. Next, execution time new is execution time old. Time, this part is actually the speed up, right? And the speed up is 1 over this part. And we also need to get familiar of those transforms and know how to calculate the speed up. The question may be, if we want like 10% speed up, how we should improve it, which part we should improve it, something question like that. Or it just directly asks you what's your speed up. Next part is mini instruction per second. Is a very simple concept. I think all you guys, you can get it. Next part is instruction set architecture. First, we need to know some basic ideas, and we need to know the data level parallelism and task level parallelism. And also, hardware exploits those classes of parallelism through instruction level parallelism, vector architecture, and GPU thread-level parallelism, and request parallelism. So for this part, I think it might be has a question like multiple choice questions to ask you some basic ideas about them. And the next part is the Flynn's taxonomy is something like SIST is single instruction stream, single data stream, SIM single instruction stream, multiple data stream, and also MIST and MIMD. It's worth to mention that the actually MISD doesn't exist commercially. And we also need to know types of architectures. There are two types of architectures. They are Van Neumann and Harvard architectures. Those two are very famous architectures, and you need to make sure you know the basic concept of them. And in Professor Slides, there is a figure for them. Make sure you can understand that figure for those two architectures. And usually they are popular questions in job interviews about these two architectures. The next part is interaction set architecture. It gives us four architectures in Professor Slides: stack, accumulator, register memory, register, and registers. Go through the slides quickly and know the basic idea of them. It will help us to understand better about the memory addressing, and it helps for us to understand the data path. So next part is memory addressing, some basic concepts like byte ordering, little ending and big ending, memory alignment. And then is memory addressing modes. It mentioned 10 modes in Professor Slides. Go through them quickly and know how to tell them when you are giving some instructions. Then is instruction set risk versus risk. It may have some multiple choice questions for this part about those concepts. And then is MIPS instruction and MIPS instruction layout. In Professor Slides, it provides us some MIPS instruction examples. There are some assembly language, but I guess you guys are familiar with assembly language. I mean some basic assembly language like add or node word, immediate add, branch, something like that. And for MIPS instruction layout, we need to know what is J-type instruction, I-type, and R-type instruction. Next part is data path. First of all, we should be very familiar with this figure on the top right. It's the basic figure for the data path. And later, when we talk about pipeline, there is another figure, but it's very similar to this one. So make sure you understand this figure and try to draw it without any help. Just using your memory. I think it helps a lot if you can do that. And for those arithmetic instruction, immediate instruction, node instruction, store instruction, branch instruction, and for each of them, Professor Ivan provides an example for them, and he draws the data path for us. So make sure you can draw those data paths yourself. I guess it will be a question ask you to draw a data path for one instruction in the midterm. I don't know, I just guess. Next part is pipeline. This lecture is also very important for the midterm and also for this class. Make sure you know the basic 5 stage, the IF, ID, EX, memory, and read back. Also this basic figure. This one is very familiar to previous one for data path, but it It just has a little more hardware, but they are almost same. Make sure you know how to draw data path. It also helps you to understand the pipeline. For the pipeline section, maybe it will be a question ask you to draw a part of this figure. I mean, maybe the professor they need the ALU or this marks and ask you what it will be here. You should draw a ALU here. Something question like that. So make sure you are familiar with this figure. Next part is hazard. There are three types of hazard: structure hazard, data hazard, control hazard. We need to know the basic idea of them and the difference between them. The structure hazard actually is the hardware conflict. Also, we need to know how to avoid those hazards. For structure hazard, we can store to wait for the hardware to be available, or we can have alternative hardware. The second hazard is data hazard. Usually it's just because the data is not ready. It has read after write, write after write, write after read. We also need to know how to avoid them. Forwarding is a very famous technology we use to avoid data hazard, and make sure you know how to draw the forwarding in these figures or in these figures, especially the left one, how to draw the forwarding in these figures. It's high likely it will be a question like this to ask you to draw a forwarding in these figures. And sometimes we cannot forward, we have to store to avoid data hazard. The next one is control hazard. Usually it's related to branches, and how to avoid that, we can move some instruction to earlier stages or to later stages, or sometimes we have to store, or we can predict taken or not taken. About the taken and not taken part, I think it will be covered in future. Okay, so this is my quick midterm review. I hope it helps. I hope you guys enjoy the distance learning, and also take care and good luck.